So in the previous video we looked at the factors of a polynomial using algebra to better understand the process of long division and finding that quotient and subsequent factors from that point onwards. What I want to do in this video is apply those ideas to a complex polynomial, and this is what a complex polynomial looks like. We've got multiple terms and some of them have real and imaginary parts to them. So what we want to try and do is we want to verify that z take 2i is a factor of this complex polynomial. That means there is no remainder if we were to divide this complex polynomial by z take 2i. And by doing that we would find the other factor. Okay, so that's what we want to do. This is a two-part question here. Firstly, verify that this is a factor, and then determine the other one, and that's using long division. So let's get into it. Here's the theory. If z take 2i is a factor, then z equals 2i, and ultimately this polynomial will equal 0 if I substitute this 2i into each one. Okay, this is similar to what we did with the algebra when we substitute a value for x in, that is when x is a root, then the f of x equals 0, or the y value is 0 because it is an x-intercept, because it is a root. Okay, this is very similar. So let's go and substitute in wherever we see a z, we are going to put a 2i in its place. So we say therefore, instead of writing z cubed, we're going to say 2i in brackets cubed, so that cubed applies to the 2 as well, plus 4 take 2i times z squared, which is 2i squared, plus 3 take 8i times 2i minus 6i. Right, and this is fairly straightforward. The only one that's a little bit tricky is perhaps this 2i squared. We're going to use distributive law to multiply those terms out, but to remember that this squared applies to the 2 as well, so this bracket is actually 4i squared, so be careful with that one. Okay, the other ones are fairly simple. What is 2i to the cube? This will be 8i cubed. So I cube the 2 and I cube the I, plus, alright, let's get in this one. This is 4 times, this is not 2i, it's because it's squared there, so it's 4 times 4i squared, so that gives me plus 16i squared. And the next term, negative 2 times, remember this is 4i squared, so negative 2 times positive 4 is negative 8. This is I cubed. So this is looking pretty good. I can kind of already see this 8i cubed is going to be deleted by this negative 8i cubed. So that's good. Remember, I want this term to add up to 0 right at the end. Plus 3 times 2i is plus 6i. Then we've got negative 8 times 2 is negative 16i squared, because it's an 8i there and a 2i, so that's 16i squared. And finally I've got take 6i. Alright, let's check if this adds up to 0. We've got 8i cubed in positive, and we've got negative 8i cubed there. We've got positive 16, negative 16, positive 6, negative 6. Yes, they all cancel out, therefore this thing equals 0. Okay, therefore yes, z take 2i is a factor. Full stop. Good stuff. So that's the first part of this problem done. Alright, let's move on to the second part. It says determine the other factor, and this is where we do our long division. Alright, normally you'd set it up nice and long like that. We write our factor that is known outside, z take 2i, And on the inside, I'm going to change this in a second, but on the inside you would normally write your polynomial, just like we did with the large algebra one. And you write z cubed plus 4 take 2i times z squared plus 3 take 8i times z minus 6i. That would be fine, but I'm going to suggest, or I'm going to show you a little trick with this. What I suggest you do is actually multiply these two terms out. Okay, using the distributive law, it just makes it a little bit simpler when you're dividing and remultiplying this in and subtracting. It sometimes is just a little bit tricky to see. If you practiced with these kind of problems, you probably not have to worry about that, but I'm going to suggest when you're learning the concept of how this works, I would multiply this thing out first. Okay, so let's simplify this thing. I'm going to write it in blue. I'm just going to write it below, or let me just move it out. So this has got nothing to do with the long division. This is simply to make this long division step a little bit easier for me. So I'm going to write this out. This is z cubed, can't simplify that anyway, plus, what is this? This is 4 times z squared minus 2z squared. Okay, so I've just expanded that out. Okay, you'll see it's much easier to work with in the long run than keeping it in those brackets, even though that might be neater. So plus 3z take 8iz. So that's okay. There's nothing wrong with that. Okay, that's just the imaginary part. Did I check? Make sure I did that there. No, I didn't. I almost missed it. Yeah, just as well saw that. Okay, so that is an I there as well. 2i z squared. So that is our imaginary part of that term. Alright, and finally I've got take 6i. So you can see it's very similar, but it is a little bit easier to work with when doing these kind of questions. So that's your first step. Okay, simplify this thing out. Alright, now we're doing the long division just like we have done with the algebra. We are only looking at this first number. Don't worry about the rest of this thing. Okay, this can be like however long. This can be z squared plus 2z minus 2i. Can be that long. Don't worry about it. You just look at the very first number. In this case, that is my z. So I'd look at my first term, z cubed, and I divide it by z. And what am I left with? Z squared. Okay, so z squared, and don't worry about anything else in here for that step. Now we just multiply this down. So use multiplication. Z squared times z, that gives me z cubed. That's good. That means when I subtract, these will cancel each other out, so that's good. But this z squared is now multiplied by negative 2i as well. So what is that going to give me? It's going to give me negative 2iz squared. Now you could write it anywhere really on this line, but I'm going to suggest you keep the imaginary parts under imaginary and the real parts under the real. Okay, and what is this going to be? This is going to be negative 2iz squared, so that's the imaginary part. Let's just keep it neat, keep it in this little column over here. So when I multiply this down, this is going to be negative 2iz squared. I know there's a bit of a awkward gap here, but don't worry about it. Okay, let's just keep everything nice and neat in the column. Remember to put a bracket around the whole term and subtract. So when I subtract, or draw a nice neat little line there as well, when I subtract, those z cubes are going to fall away, so I get 0 there, and I've got a negative 2iz squared, and I'm going to subtract a negative 2iz squared. So this is going to be effectively adding 2iz squared, so that leaves me with 0 for that term too. Okay, and basically now I just write down what am I left with. So I bring this term down. It didn't get changed, so I have 4z squared plus 0 plus 3z minus 8i z minus 6i. Okay, that is the full thing. Do you need to write all this? No, you probably don't. Okay, you could leave it off if you wanted to. I just did write it down then, just for neatness, I guess. Alright, again, I rinse and repeat. This z goes in here, so divide the 4z squared by z, and what am I left with? I'm left with plus 4z. Okay, and multiply down. Don't worry about anything else for that first step. Multiply it down. 4z times z is 4z squared, so that's good. And 4z times negative 2i is negative 8i z. Okay, and again you can see I've kept that in this imaginary column for the z to the power of 1. So that this is always kind of staying the same. Nice and neat. Put it in brackets and subtract. What am I left with here? 0. And here I'm left with 0 again. So you can see a bit of a trend here. It is deleting that other every second term for me, which is quite good. Alright, I am still having to bring down this 3z and this negative 6i, so that's what I'm left with for my third row of calculation. 3z take 6i, like that, and do my last long division step here. 3z divided by z gives me just plus 3, and multiply down. 3 times z is 3z, and 3 times negative 2i is negative 6i. Draw a line, subtract, and make sure that there are no remainders, and that's good. That's exactly what we expect. There are no remainders. Okay, and that means that we've done everything correctly, because we've said, or we've shown in the previous step, that z take 2i was a factor. So when I do this long division, I should have no remainder, and that's what this is showing me. There's nothing left. We've brought everything down, and we've subsequently found the quotient, or the other factor, and this is a trinomial factor of this complex polynomial. It has 3 terms, okay? So therefore, the other factor is z squared plus 4z plus 3. Okay, that's a fairly large factor. Would be quite nice if we could perhaps factorize that even further. Can we factorize that even further? Could we say, which is actually, if you look at that, you can actually factorize it. You could say that is z take 3, z take 1. Okay, that if I multiply that out, is that correct? No, it's not. That's plus and plus. So there. Now when I multiply that out, I get that same factor over here. So that left hand side equals right hand side. Therefore, the 3 factors, this is not really what the question is asking me, but let me state it anyway, because I can for this one. Oh, don't forget this one that we found here, or verified. It is z take 2i, z plus 3, and z plus 1. Okay, so those are the 3 factors of this complex polynomial. I hope that all made sense. And in the last video that I'll do for you guys, I will show you what do we do if this factor is not given. Very similar to what we did in the algebra. Okay, this is not given. You have to do a bit of guess and check to try and find that first factor, and then do the exact same process. So that'll be in video 3.